Welcome to Fishing for Mercury by Colegio Franklin Delano Roosevelt. We are the only high school team in the entirety of the Southern Hemisphere, which means we're also the only high school team in Latin America. This creates specific challenges for us, such as having to drive an hour and a half both ways just to be able to get to our lab. And so, yeah, here's Kia to present the beginning of our project.
Along the coast of Peru, there are high concentration levels of plankton, which small fish like anchovies feed. Therefore, we have the highest amount of anchovies in the world. An industrial use for anchovies is fish meal. Fish meal can be used to feed other animals, which will be later consumed by humans. 41% of all fish meal in the world come from Peru. This is a portion of the Amazon that has been destroyed by illegal mining. In the last 20 years, more than 3,000 tons of mercury have been dumped into the Amazon River by this illegal activity. The mercury finds its way into our food supply through the anchovies. Mercury is a neurotoxin that is declared by the World Health Organization as one of the top 10 chemicals of major public health concern. Mercury can build up in living tissue through the process of bioaccumulation. Contaminated fish meal distributed throughout the world will end up in our system because of this. In order to make our solution, we visited TASA twice this year, the largest fishing company in the world. We learned about the fish meal production with the scientists, and they told us about this process, and we asked them if they would be interested in a methodology of heavy metal removal. We then worked with Universidad Cayetana Heredia to further design our solution, and also they all offer lab work there. Our resulting solution is to modify bacteria to detect and remove mercury by transforming it with two different constructs. And as you know, this process will yield many bacteria with the same unique characteristics. To implement our solution, we created a container prototype, which will make the bacteria and also the fish will interact. The idea is that once the bacteria have crossed the sieve, the wired sieve, they cross over the sieve, which prevents the fish meal from passing through, and the bacteria die upon exposure of light. Now my colleagues will explain the science behind this.
So, in order to solve the problems created by mercury contamination, we had to accomplish two tasks. Our first task was to accumulate the mercury found in the fish meal. Then, we wanted to induce suicidal bacteria following the mercury accumulation in order to later collect the bacteria. So, to isolate mercury from the environment, we had to design a method of trapping it from the fish meal. We achieved this through the use of a mercury accumulator device created by the 2014 UFAM Brazil iGEM team. Our plan was to add GFP to the accumulator part in order to have a simple method of visualizing whether the ligation or the transformation is successful. Furthermore, it could help us detect when the fish meal becomes mercury-free, as green fluorescence protein will no longer be expressed in the future generations of the bacteria. But we are still developing a method of overlap extension PCR to insert it into the accumulator part. Thus, for our future experimental tests, we used the original accumulator. Because fish meal is used in agriculture and aquaculture, we wanted to make sure that no live bacteria would be found in the fish meal after it's been processed. So we added a suicide construct that produces killer red protein in the presence of mercury and light. Killer red reacts with light to produce highly cytotoxic reactive oxygen that results in bacterial death. Furthermore, additional heating processes in the factory protocol would ensure the death of any stray bacteria that was not in contact with mercury or light. So our construct is a double-conditioned suicide device composed of several iGEM parts. The first condition is the presence of mercury, and the second condition is the presence of light. We included a mercury-responsive promoter. Then ribosome binding sequence. We chose this ribosome binding sequence because it has a moderate binding strength to slow down the expression of killer red in comparison to the accumulator. We wanted to allow the bacteria time to accumulate mercury before expressing killer red and being subjected to the light. Thus, this consideration for the RBS binding strength. Following the RBS part is the killer red part, and then it's a double terminator. So, in order to create our construct, our plan for ligation was to start with a double restricted promoter using XP1 and SP1, ligate them together, and then follow the same process to create our final construct. But we had to change our plan. So we encountered two challenges when working on the ligation. Our first obstacle was in isolating the promoter when they were using the restriction. After the restriction, we could not detect the promoter inside the gel, despite using 1%, 2%, or 4% agarose. We hypothesized that the concentration is too low, therefore we tried a PCR wash to increase the concentration. However, we could never detect the promoter. And we knew we'd have trouble with the RBS sequence since it's even smaller. Our second obstacle is that we ran out of SP1 enzyme. As mentioned before, being located in Peru presents its challenges. Our PI asked around all of the Latin lemma, and none of them had SP1 enzyme. And it would also be difficult to ship it to our country for the strict custom regulations and the high price. So for our solution was to just send our DNA sequence to IDT to get it synthesized. Using SnapGene software, we designed our construct as if it were ligated. We took the sequence of the parts from iGEM registry and arranged them in order. So promoter, RBS, killer red, and the terminator. In between each sequence, we added the ligation scars of XP1 and SP1 enzymes. But we decided to switch the ligation scars with ligation sites, flanking the RBS to HIN3 restriction site and AP1 restriction site. And this would serve two purposes. First, to provide a method of checking whether or not the ligation is successful, and to facilitate future characterization of the part of different RBS to delay or promote the expression speed of killer red. So even though we haven't fully tested it, these two plasmids are designed to work in conjunction to each other inside the bacteria. Accumulate mercury and then killing itself.
After the construct was ligated with the plasmid and transformed into the bacteria, we assessed whether the ligation was successful and whether or not the bacteria could grow in the presence of mercury. In this gel, we can see the results of restriction reactions on our killer red construct. In well 5, the plasmid was cut with a HIN3 enzyme, a restriction site that we added in next to the RBS. On the right is a restriction using a BAM-H1 enzyme, a restriction site that was already present in the iGEM vector. We see the products of both restriction reactions are the same size. And so this is the first piece of evidence that our construct was ligated with the plasmid. Here are the results for our transformed bacteria growth in the presence of mercury. Here we incubated transformed bacteria in the presence of varying concentrations of mercury. On the left, you see a growth curve for bacteria transformed with our killer red construct. And on the right is a growth curve for bacteria transformed with the accumulator. We see that transformed bacteria do grow in the presence of mercury. However, the bacteria must be allowed a growth period of 60 to 90 minutes before incubation with mercury. You can see that bacterial growth is inhibited by the presence of mercury. However, we are still standardizing the protocol for appropriate incubation times and concentrations of mercury. And here are our future steps. The first of which is to finalize the GFP addition to the accumulator. Secondly is to standardize our incubation protocols with mercury. Thirdly is to characterize killer red expressions under different RBSs. And finally is to transform both of our constructs together and determine efficacy of accumulator and killer red working together. And now my colleague Sky will introduce the hardware.
In order to implement the solution, we decided to create a container that could potentially be added in the fish meal production process.
It was essential for our project that we had industrial application. And because of this, we chose the following conditions that we felt that we knew had to be met. The container must allow for bacteria and fish meal to interact, bacterial growth, bacterial function, and isolation of mercury.
The current design is rectangular and has a sieve vertically placed in the middle. This, on one side of the container, you can see that there's a motor that will facilitate the water circulation. The sieve will only allow bacteria and water to go through. It doesn't have fish meal to go through. And when bacteria ultimately goes to the other side, it will die because there's a light with 540 nanometers in wavelength that will activate the killer rat protein in the bacteria. We still have to check if that bacteria, having lost mobility, is more likely to sink. If it actually sinks, it would be really helpful because the fishing companies would actually be able to just clean it up really easily and pick it up from the other side of the container. To be able to attach our sieve to the actual container, we 3D printed a holder made of PLA filament. We use PLA filament because, unlike other plastic, it is biodegradable, and it is mostly made of cornstarch. And for that reason, it doesn't have many of the chemicals that could potentially harm bacteria.
So we went through several iterations of sieves. We started with a nylon cloth that we had to get from stockings, but quickly realized that this did not work very well. We then tried cheesecloth, which was better experimentally because we were able to add and take away layers depending on what we needed, but this also was not very effective. We finally ended up with 90% polyester and 10% spandex fiber cloth that we had to get from a pair of unused underwear. This was the most efficient cloth that we could find, and it was able to sieve everything properly, but we did find some issues with the sieve holder that we were using, so we just fixed it with a silicone seal or hot glue.
We incubated all three of the materials, PLA, plastic, silicone, and spandex, with the bacteria to make sure that they weren't toxic. And as you can see, none of them are toxic to bacteria.
So the whole point of this project is to isolate mercury from fish meat and separate it. So we're using bacteria to transport the mercury from one side of the sieve to the other side of the sieve without the fish meat. And there, we would induce suicide in the bacteria so that it would drop and therefore not move. And in order to understand the motion of the bacteria, we had to analyze the forces that were at play. And there are three forces that are in all of the bacteria, which is the force of weight, the force of buoyancy, and the force of drag. But the difference lies in one, the position, the distance from the motor, because there's close to the motor there's a force of 22 millinewtons, and closer to the sieve there's a force of 12 millinewtons, and on the other side of the sieve was so strong that in fact there was 0 newtons. And the other difference is that there's the flagella. So once the bacteria dies, it would no longer have the force of the flagella occurring. And so, as of right now, we're still trying to find the critical point in which we should kill the bacteria so that it dies and does not go back to the other side of the sieve. That's something that is in our next steps.
So in order to test that the water was circulating entirely, we put blue and yellow color dye on opposite sides of the sieve. We then used a colorimeter testing for green absorbance at 550 nanometers on both sides to find when the water is actually the exact same color. This tells us when the water is all the same color, it tells us that all of the water is able to circulate, and we were able to calculate that it took 19 minutes for all of the water to be the same color. And as you can see on the picture on the right, there's no difference because it's the same color. And so we also had to test that the fish meal wasn't going through either. So to make sure that it wasn't, we put it on the side with the motor, let the motor run, and then we tested the opposite side of the sieve at 600 nanometers with a spectrophotometer. And every single minute, we just tested the light absorbance. And then we got all results of either 0 or negative. The negative numbers mean that there is a slight margin of error, and the 0 means that there's no fish meal going through.
In order to make sure that the bacteria was going through the sieve, we actually conducted a growth curve. What we did was place bacteria on the motor side of the container, and then we grabbed samples from both sides to see what was the reproduction rate. And as you can see here, it reproduced at the same rate in both sides of the container, demonstrating that the bacteria was actually going through.
As tends to happen in scientific research, we still have a few important questions in mind. Right now, we want to find out what is an effective way to isolate the dead bacteria, fish meal, and mercury after running more experiments. And 2, what is a more effective tank shape? And what our next steps would be to print a 3D printed prototype tank that would fit these conditions, then run more tests with a light factor, and keep investigating.
Because very few people in Peru are aware of synthetic biology, human practices is a crucial part of our project. The first 2 projects were created to inform others about iGEM, and the last 2 were created to give children basic science education. The Journal of FDR Science was used to market our iGEM project and the relevance of mercury contamination in our local community. The article topics included range from the health effects of mercury to exploring heavy metal mines in Peru. And this journal is currently published on our school newspaper. Then we created an infographic to inform others. We created 2, one to inform fellow high school students and teachers about our project and the science behind it, and the other targeted university students at La Universidad Nacional Agraria and La Universidad Peruana Cayetano Heredia, our country's best universities in the fields of agricultural and biological science, in order to help them know what iGEM is and encourage them to create a team of their own.
It is very hard to get a good scientific education in English in Peru. Testament to this, the program for international student assessment has ranked Peru last in the categories of reading, science, and maths. This is why we decided to collaborate with Alva Roosevelt. Alva Roosevelt is our school's most renowned community serving club. And on a normal day, on Saturday, students go from 9 a.m. to 12 p.m. to campus to teach the workers' children English. We have introduced 7, up till now, lessons in the sciences, each 90 minutes long, ranging from topics from light, friction, chemical reactions, and more. And this allows kids to take part in fun scientific lessons and learn English along the way. We have already seen an impact on the kids' proficiency in English and knowledge of the sciences through the testaments from the kids and their parents. And if we continue this project, we hope that this has a permanent impact on the kids' lives. Girls Can is a student organization in our school that aims to solve the disparity between men and women in the field of sciences later on. And we have developed lessons for girls in elementary school through a social issues curriculum, a few relief activities that used to solve local problems. We hope this will help girls transition more better into elementary school, into middle school sciences after the elementary school curriculum in sciences kind of weak in our school, and of course bridge the gap between men and women in the advanced sciences later on in their lives.
Throughout our project, we've had many collaborations and many people we have to thank. First of all, as Kia mentioned, we collaborated with TASA, who donated 2 kilograms of fish meal for all our wet lab and tank experiments. Then we collaborated with La Universidad Peruana Cayetano Heredia, where we conducted all of our tank and lab experiments for our project. Finally, we collaborated with the Argentine Uchile Biotech, who created a magazine called LATAM, where they displayed all of the iGEM projects over Latin America, and we contributed with information about our project and its implications, and they in return helped guide us through the creation of the Journal of FDR Science. We would like to thank specifically Daniel Guerra, Keren Espinosa, and Pierre Bahia for guiding us throughout the whole project and teaching us a vast majority of what we know. And we especially need to thank our instructor, Dr. Nina Markham, who has challenged us throughout this whole season. Finally, iGEM has brought synthetic biology on a high school level to Latin America, and it has allowed us to pursue our passions. And so in conclusion, we thank you, Keren, Dr. Guerra, Dr. Markham, and finally, iGEM.